Welcome to OGUS Training. OGUS is an integrated training platform for process engineering in upstream oil and gas sector. In this educational and training video, we will talk about the operational problems commonly faced while operating centrifugal pumps. In oil and gas facilities, centrifugal pumps are often the hearts of the plant. They have myriad applications, from the main crude oil pump, to the main sales pump, utility pumps, fire water pumps, or process fluid pumps. We see centrifugal pumps everywhere. You will find a lot of materials over the internet that beautifully explain the construction and working of the centrifugal pumps, but there are few resources that explain the operational problems and troubleshooting steps for these machines particular to the oil and gas industry. Let me remind you that even though we concentrate on the oil and gas industry, the theories presented here will apply equally well in other industries also, and one can certainly use these as practical examples and troubleshooting guide for any applicable case. The major operational problems that we face with the centrifugal pumps in the oil and gas industry are: 1. Pump damage due to cavitation. 2. Pump damage due to operation at lower or higher flow than what is specified in the performance curve. 3. Damage of self-lubricated pumps due to solid impurities in the process fluids. 4. Pump damage due to vibration induced by the recycle flow control valve. We will explain all these problems in detail. Let us consider a centrifugal pump pumping hydrocarbon liquid, say crude oil, from a tank which is full up to a height of h meter. The crude oil has a density of d kg per cubic meter, so the pressure exerted due to the static head is, in the unit of Pascal, h multiplied by d multiplied by g, the gravitation acceleration. Let us assume the pressure in the tank vapor space is P tank in the unit of Pascal. When the fluid moves through the suction pipeline, it experiences some pressure drop due to the resistance exerted by the pipeline. This resistance is enhanced due to pipe roughness, presence of fittings and sharp bends and changes in pipe diameter. There will also be some pressure drop when the fluid moves through the suction strainer. The fluid experiences some pressure losses while it moves through the pump inlet up to the eye of the pump impeller. Accordingly, the equation for the fluid pressure at the impeller eye is written as pressure at pump impeller eye is equal to tank pressure plus static head minus pipeline pressure drop minus strainer pressure drop minus drop in pump inlet. In case the pressure at the eye of the pump impeller falls below the vapor pressure of the fluid, part of the fluid will turn into vapor, giving rise to formation of bubbles in the fluid. These bubbles collapse as soon as the fluid passes to a region of higher pressure, that is when the fluid comes out of the impeller and moves to the pump volute casing. These collapsing bubbles send numerous high-velocity microjets and pressure shock waves, leading to erosion of the impeller material. Cavitation also leads to high vibration that damages the pump components, the most vulnerable part being the pump seal. These pictures show us how pump cavitation can damage the pump components. The pressure at the pump suction minus the fluid vapor pressure is called the net positive suction head. We have two different terms, net positive suction head available which is denoted by NPSH suffix A, and net positive suction head required which is denoted by NPSH suffix R. NPSH A is the actual head available at the pump suction. The NPSH-R is the minimum head required at the suction to ensure that the liquid will not turn into vapor at the pump impeller eye. The NPSH-R is obtained from the pump vendor data sheet. The NPSH-A should always be at least 10 to 20% above the NPSH-R. Many liquids that we work with in oil and gas industry, like LPG, natural gas condensate or petrol, have high vapor pressure, that is they turn to vapor easily. Crude oil being a mixture of different components, the lighter components show tendency of giving rise to good amount of vapor while moving through pipes. Moreover, the gases dissolved in these liquids, especially crude oil, may vaporize and give rise to bubbles in the pump suction. Pump cavitation can be detected by abnormal noise and pump vibration. Let us try to understand the phenomena of cavitation in a centrifugal pump in more detail. We express our sincere thanks and gratitude to IET for this part of the video.
Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as the flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function.
To eliminate cavitation, follow these steps. 1. Reduce pressure drop in the pipeline by cleaning possible blockages in the suction line. 2. Reduce number of bends. 3. Check all the valves are open fully. 4. Ensure sufficient liquid level in the tank. 5. Ensure the pump is being employed to pump a liquid of same density, composition, and boiling point as designed. Oftentimes, while starting a pump, we find that the pump casing is full of air or vapor. Centrifugal pumps cannot push the vapor out by themselves, so if we start the pump without first taking the vapor out, the pump starves of liquid, and this can lead to serious damage of the pump internals. The way to overcome this problem is priming the pump by opening the suction valve and letting the liquid fill the pump casing until a steady stream of pure liquid, without any gas bubbles, come put through the top vent port or priming port on the top of the pump casing. In case of handling hazardous fluids, it is recommended to divert the liquid stream to a closed drain system. This is an example of the performance curve of a centrifugal pump at a certain impeller diameter. It is imperative that the pump is always operated at higher than the minimum continuous flow. When a pump is operating at the best efficiency point, flow through the impeller is very stable and uniform. However, as the flow produced by the pump decreases and the operation of the pump moves to the left of BEP, some of the liquid begins to move in a circular pattern. It enters the impeller inlet but then comes back out of the inlet and then is drawn back in again. This circular and irregular flow pattern is known as recirculation. The more flow is reduced, the greater the amount of recirculation within the impeller inlet. Once recirculation becomes excessive, it will result in increased vibration and pressure pulsations. Pump manufacturers make a determination, based on engineering analysis and experience, and establish the minimum flow that must be established to avoid excessive recirculation. This minimum flow point is called the minimum continuous stable flow. In the same manner, the pump head drops suddenly after certain high flow point, which is the end of the performance curve. The pump must never be operated beyond the curve. Trying to run a pump off the right end of the curve will result in pump cavitation and eventually destroy the pump. The suction and discharge pressures fluctuate wildly, pulling and pushing the impeller about because of the out-of-balance forces. The shaft rattles, mechanical seals are damaged, packing is worn, bearings are destroyed and shafts are bent. Pumps will be noisy, vibrate and shake, get hot, and the microjets of liquid ejected by imploding bubbles will hit and erode the impeller metal. To ensure sufficient flow is passing through the pump, a recycle flow control valve is often fixed which recycles a part of the pump flow back to the tank or vessel at the pump suction. This ensures that the pump always delivers the minimum required continuous flow even if the pump discharge valve is throttled for process requirement, say for controlling the tank level or the discharge flow. In most cases, the centrifugal pump internal parts are lubricated by the process fluid itself. In case the process fluid is carrying a lot of solids and the strainer at the pump suction is unable to filter out all the solid impurities, the pump internal parts, especially the bearing and seal, will be damaged due to abrasion. We discussed the recycle control line that is used for ensuring that the pump always delivers the minimum required continuous flow. Sometimes when the flow through this control valve falls below a certain value due to the valve throttling, the valve starts vibrating. This is due to a phenomena called cavitation in control valves, which is caused due to partial vaporization of liquid when it passes through the very small aperture in a control valve that is almost closed. In many plants we find two centrifugal pumps running parallel, one in duty, the other standby. In such systems, if one pump has its discharge non-return valve passing, the flow from the other running pump will come reverse to the standby pump and will force the pump impeller to rotate in reverse direction. This type of reverse rotation puts undue stresses on the pump components like shaft and bearing and cause damage over long time. Moreover, the running pump consumes high current as its flow increases beyond capacity, because a large part of the flow it delivers goes back to the suction line through the standby pump. We hope you liked this video. Do leave your comments and subscribe to our channel for more such informative videos.